Yes. So we were talking about the importance of metals in our daily lives, right? And about the unique properties of the metals with which they are characterized, right? I told you metals are having very good common physical properties, like they have great strength, they have high density, they have good electrical and thermal conductivities, and high optical reflectivity, right? Okay, so we can say that metals are characterized by uh, strength, they are characterized by high density, they have good electrical and thermal conductivities, and high optical reflectivity. Okay, so these are the characteristics of common characteristics of metals. Now, it is very important to explore and understand the properties of these materials so that they could be utilized for the technological applications. So, in this chapter, we shall study some important transport properties of the metals. We shall see that how these properties are intimately related to each other, and they can all be explained by assuming that a metal contains large concentration of free electrons which are able to move freely throughout the crystal, right? This is very major characteristics, very important characteristics of the metals, that they are characterized by the high concentration of free electrons which can roam around the metal, and which can provide the unique properties to the metals, right? So let us first understand what are these conduction electrons, or what are free electrons. Or you can say what are free electrons. Okay, so in order to understand the concept of free electrons or conduction electrons, let us take an example of sodium metal. Do you know how many electrons are there in sodium? Anyone? What is the atomic number of sodium? Any one of you?
11.
Yes, yes, yes. So the atomic number of sodium is 11. Now, if I ask you that if 11 is the atomic number of the sodium, then how many free electrons should be there in the in sodium? Can you answer me? No. Yeah, yeah, only one, only one. But in case, suppose if I give you let's say 50 sodium atoms, can you tell me how many number of free electrons there are there?
50.
Yeah, it will be 50, right? Because one sodium atom is donating only one free electron in the entire volume, right? So it means that this is a monovalent metal, this is a monovalent atom. So it is donating one free electron, means the number of free electrons will be equal to the atomic number of the sodium, right? So if we see the going into very elementary part of this, if we see the electronic configuration of sodium, it should be 1s2, 2s2, 2p6, and 3s1. Okay, so we can see that all the internal orbitals of the sodium are occupied. However, there is only one electron which is unoccupied and which is in the outermost orbit, right? So this one S1, this one electron is the free electron. This is the free electron. In other words, you can say that this electron is not bounded to the entire system, but it can roam around, it can move from ion to ion, from one ion to another ion, right, throughout the volume of the metal, right? However, it cannot leave the surface. Why? Because of the surface potential, right? It cannot leave the surface of the metal because of the surface potential. So it is bounded to the surface, but it is free to move in the bulk of the metal. Okay, so see, this is the situation when we are talking about the free electron model. If the atoms are, see, in this case, we are assuming that all the atoms, they are not tightly bounded, they are free, they are behaving like a gas, right? So in that situation, the atoms will be far apart from each other, right? However, if we bring these atoms together in order to form a solid or in order to form a metal, then there will be overlapping of the atoms, like this, right? So if, let's say, this is the outermost orbit of one sodium atom, this is the outermost orbit of another sodium atom, this is the outermost orbit of third one, and this is the outermost orbit of fourth one, then you can clearly see that this particular electron, this is the outermost electron, right? This particular electron is not bounded to one atom only, but as a whole it is bounded to the other atoms also. See, you can say this is overlapping, so this is bonded to this also, right? Now since this is overlapping with this one, so this is bonded to this also. So we can say that the free electron as a whole is is bonded to all atoms of the system. All atoms of the system, right? So we can say that the electron is bonded to entire bulk of the metal and it is free to roam around the bulk. Okay, so now what happens when this particular metal is applied with a external electric field, then these free electrons, they will drift along the direction which is opposite to the applied electric field and they will constitute current, right? So that's why the metals, they are having high electrical conductivity because they are having high concentration of free electrons. Okay, so this is about the conduction electrons. Now we are going to talk about few characteristics of the metal and then we will derive the electrical conductivity of metals. Okay, so let us jump to some very important characteristics of metals. So some of the important characteristics of metals are, number one, they possess high electrical and thermal conductivities, as I told you. They possess high electrical and thermal conductivities. Number two, they possess, metals possess Ohm's law, you know that. metals possess Ohm's law, which states that in steady state, the current density J is proportional to the electric field. The current density J, this is current density, is proportional to the applied electric field. Or you can say that J is equal to sigma E, where sigma is the electrical conductivity. Where sigma is the electrical conductivity of the metals, right? Okay, so third very important characteristic is the conductivity of metals decreases with increase in temperature. The conductivity of metals decreases with increase in temperature. Decreases with increase in temperature. Okay, you should know why this happens. Do you know why did this happens?
Because
yeah.
Because when we increase the temperature of the metals, what happens is there will be so much, means the motion of electrons will be very, very fast. So, due to which the resistance of that particular metal, or we can say conductor, increases as the relaxation time is less and the number of collisions are more. So, that's why the conductivity decreases.
Yes, that's true actually, because the randomness in the system increases actually, right? So as a result, the number of collisions in the system also increases, and hence the conductive resistivity will increase. So therefore, the conductivity will decrease. Yeah, that is true. Okay. Then fourth characteristic is metals obey Wiedemann-French law. Metals obey Wiedemann French law. Okay, this law states that the ratio of thermal conductivity and electrical conductivity at a given temperature is equal, is small for all metals and is proportional to the absolute temperature, right? So you can say that if K is the thermal conductivity, if K is the thermal conductivity and sigma is the electrical conductivity, sigma is the electrical conductivity, then this ratio of K is to sigma is directly proportional to T, or you can say that K upon sigma T is equal to constant. K upon sigma T is equal to constant. Okay, so these are four important characteristics of matters. कई बार एग्जाम में भी पूछा जाता है आपको explain the important characteristics of matters. So these are the four very important characteristics of matters, right? So after this, we are going to jump for the derivation of electrical conductivity of matters. Yeah, is it clear? Any doubt? Any doubt to any student?
No, ma'am.
Okay. Okay, great. So now let us go for the derivation of electrical conductivity of metals. Electrical conductivity of metals. Okay, so as I told you, the there are number of the concentration of free electrons in metals is quite high, right? And the phenomena of electrical conductivity, due to the high concentration of the free electrons, there is a high electrical conductivity and thermal conductivity of the metals, right? So in order to explain the electrical conductivity of metals, we will consider that there is a sea of free electrons within the metal, right? Or we can assume that the metal as a perfect gas. Okay, so what happens in perfect gas? In perfect gas, all the molecules, they can roam around, they are free to move within the enclosure, right? And there is a random velocity, there is a random direction of all the molecules. So same model we are going to adopt for the free electrons. We will assume that the free electrons, they are behaving like the molecules of a perfect gas, and they are free to roam around, they are free to move with any velocity, with any in any particular direction. Okay, so we are comparing the free electron model with the perfect gas. Okay, so the phenomena of electrical conductivity in metals, it can be explained very well on the basis of electron gas model, according to which the free electrons in metals behave like molecules of a perfect gas in a container. So it was Drude in 1900 who put forward a simple theoretical explanation of electrical conductivity of metals based upon the electron gas model. So it was Drude in 1900 who put forward this model, and there are few assumptions of this model, and we are going to discuss those assumptions one by one. Later on, this Drude model was slightly modified by Lorentz. So the name of this model is Drude Lorentz model, or theory you can say. So the assumptions of this model are: number one, there are large number of free electrons in the metal. As I told you, the electrons are free to move about the whole volume of the metals, just like molecules of a perfect gas. The electrical or thermal conductivity of the metals is only due to these free electrons, right? So this was the first assumption of Drude Lorentz theory, that there are large number of free electrons, and they are behaving like perfect, like molecules of perfect gas. They are behaving like molecules of a perfect gas, right? So this was the very first assumption of Drude Lorentz theory. Second assumption was uh, free electrons in metals move randomly in all possible directions, right? So free electrons move randomly in all possible directions. In all possible directions with widely different velocities. With widely different velocities, like molecules of a perfect gas. Like molecules of a perfect gas. Okay, and the distribution of electrons is in accordance with the Maxwellian distribution for a gas. Like how these electrons are distributed within a atom, so it can be determined, the distribution, it can be determined by using the Maxwellian distribution. You might have studied in the statistics part. Okay, so the distribution is Maxwellian distribution. Okay, so this is the second characteristic, this is the second part or second point of the Lorentz Drude theory. The third assumption is free electrons make collisions from time to time with fixed positive ions in the lattice and also among themselves. Okay, so they make collisions free electrons make collisions with positive ions in the lattice, positive ions in the lattice, and also among themselves. And also among themselves. So if let's say if this is the lattice of ions, free electrons, they will collide with the positive ions, and there must be a sea of electrons also, right? So they keep on colliding with themselves as well as with the positive ions. Okay, so fourth assumption was in the absence of an external electric field, the random motion of free electrons is equally probable in all directions. As a result, the current density vector is 0 in the absence of an electric field, right? So a question might be there in your mind that if there are so many free electrons in the metals, why they are not possessing the electric current? So this is the reason, that because these electrons, they are randomly distributed and their velocity vectors are also random. Okay, for example, this is having this this direction, this electron will have this direction, so there will be another electron who is having exactly opposite velocity to this. So the density vector, the velocity vector, they are going to cancel each other, and as a result the net velocity or the net movement of the electrons will be 0, right? So therefore, in the absence of any electric potential, in the absence of any external electric field, there will be no current density vector. The net current density vector will be 0. Okay, so you can say the net current density vector is 0 in absence of any external field. So this is the fourth assumption. Fifth assumption is when an external electric field is applied, the electrons drift slowly with some velocity known as average drift velocity. So the direction will be opposite to that of the applied external field. You know that the direction of electrons is always opposite to the applied external field, right? So what will happen when these random electrons, when they are given an electric field, they will drift along a direction which is opposite to the direction of electric field. So if they are the electrons, you can say they are randomly distributed and their velocities are also random initially in the absence of electric field, but when the external electric field is applied, then what happens that they start drifting in a direction which is opposite to the direction of the electric field. So now the direction of these electrons will change, they will align themselves in a direction opposite to the direction of the applied electric field, and as a result they will constitute current. Okay, so the electrons drift in a direction opposite to the applied external field E. Okay, so this is the fifth assumption. Sixth one is, in the presence of external electric field, the free electrons being accelerated gain some additional kinetic energy, right? What happens when this electric force is applied to these electrons? They will be drifted, and obviously they will be accelerated and will gain some kinetic energy, right? The accelerated free electrons on collisions with the positive ions fixed in the lattice lose its additional kinetic energy, right? When they are accelerated and when they gain some kinetic energy, they will collide with the positive ions, and here some energy will be lost. Okay, so this kind of collision, this is called inelastic collision. Just after, see this, for example, let us talk about this particular electron, and here it is a positive ion. So when it will gain some energy through the external applied field, it will collide with the positive ion and it will lose some energy, right? And this kind of collision, in an inelastic collision, will occur. Inelastic collision with the positive ions. Inelastic collision with the positive ions. Okay, now what will happen just after this collision? Just after this collision with a positive ion, the electron will again have random motion for a moment, right? After colliding with this positive ion, maybe the direction will change, and let's say this is the again the direction of the,
फिर जियो ऐसा ही हो गया जैसा था 2 साल का रिचार्ज फ्री है
yes students, please mute your microphones.
ऑनलाइन ना है तो करना वैसे मिलेगा
Students, please mute your microphone. There is a disturbance in the class. Yeah. So after colliding with this positive ion, the electron will again be drifted. It will again be accelerated. It will again have some random motion for a moment, right? But due to the external electric field, now because this electron is under the influence of the external electric field, so what happens again, by the influence of this electric field, this electron will again be aligned in a direction which is opposite to the direction of the applied electric field, right? So this process, in the presence of electric field, this process of inelastic collisions of free electrons with the positive ions continues. So this was the sixth one. Seventh assumption is the average distance traversed by a free electron between two successive collisions with the positive ions is known as the mean free path. You know that, right? For example, say this is the positive ion, this is the positive ion. So let's say an electron is first colliding with this one, and after inelastic collision the electron is colliding with this positive ion. So the distance between these two collisions is known as the mean free path lambda. Okay, mean free path. Okay, so these are the assumptions. Now